in Michigan in the departments of movement science, biomedical engineering, and robotics. She did her PhD in 2009 in bioengineering in the University of Texas in Austin. Before she became an engineering consultant and then moved on to a research position at the military clinical Gates clinic.
Yeah, clinical gait lab, yeah.
And then she became faculty at the University of Michigan, where she's now directing the Rehabilitation Biomechanics Laboratory. And her work focuses on the biomechanics of people that use upper and lower limbs prosthetics. And specifically, she's looking into these repetitive movements, like in walking and reaching, and which aspects of those movements are controlled directly by the keyboard. And she will tell us more about her work here. But before Deanna will give her talk, I would like to remind you that there is a reception after the talk in 1507. You are all invited, and I hope you all come.
Awesome. All right, thank you. All right. So, as she said, my work really focuses on understanding how people use prosthetic devices, and we look at both upper and lower extremity. And the big key here is that there's this combination of factors that's going to enhance human performance, and that's really related to the design of the device. So that's sort of mechanical design, but also control. And this control question becomes really important, I think, in prosthetics. So how are you going to actually control this device, especially when you add more degrees of freedom to it? We also look at the human characteristics. So what about that individual predicts how they're going to succeed with the device? And then in the interface as well. So this is a robotic device that has to be put on the body, and you have this attachment point. And how that attaches to the body is really integral to how it succeeds. So the rest of our work really focuses on the, how each of these factors lead to improvements in performance. So while I do upper limb work as well, I'm going to take you on a journey through the ankle today. So how I got interested in ankle design, how we evaluate the success of these kind of devices, how we optimize their performance, and then are there different ways that we can approach the control problem. So in terms of this issue, I think probably many of you know, but amputation is a large problem. That there's about 1.6 million people in the US with amputation. I mean, this number is slightly old, and this number is actually much larger now, and it's growing, mostly because of increase in obesity has led to increase in type 2 diabetes, which decreases the sensation on the base of the foot. And so what happens is, without that sensation, people have develop sores and infections, and that progressively leads to amputation when those sores get worse. And so that actually is a huge growing population, especially what we see in Michigan. And so this is a large growing group. And there's also the population from the military. And so there's estimates that there's about 1,700 amputations that have resulted from just the recent conflicts in Iraq and Afghanistan. And so while these individuals can be successful, they can go back and they can do, and they can walk and they can engage in their environment, they do have several limitations. One of those is that it's more energetically costly for them to walk. It's also, they tend to walk at a slower speed, so they prefer to walk slower. And they develop asymmetries in the movement pattern. So once you've lost this musculature, you aren't able to directly replace it with the prosthesis, and therefore the movement itself becomes more asymmetric, and the loading is also asymmetric. And this is really problematic because it can lead to a lot of secondary health problems. So in this population, you have an increase in obesity, increased prevalence of cardiovascular disease, so they tend to be less active. And it's thought it's because it's more energetically costly for them to walk, so they're less active. And they also have high incidence of osteoarthritis and low back pain. And so those can come from the asymmetries of the movement pattern. And so when I got interested in this is about 2002. At that time, prostheses were pretty much they're all passive devices. Everything that you can see here, there's tons of options for them, but generally they operate in the same way. So this is a carbon fiber system, and as you hit the ground, it stores energy, and then it releases some amount of that energy as you come off of the ground. So they're not ideal for necessarily all terrains or all activities. And what the clinician has to do is choose a single stiffness that replaces the function of the biologic ankle. So you're replacing the musculature and the tendons with this single stiffness. And so if you choose poorly, this can lead to increased metabolic cost, abnormal muscle activation patterns, and then further decreases in symmetry. And so what we thought was, okay, let's think about why couldn't we make multi-stiffness feet? And so this is an example of how you actually do that. So in this case, it's important to look at how do you actually quantify what the stiffness of the foot is. And so you can see this is an ankle moment and ankle angle curve. And the slope of this line represents stiffness of that complex. We call this quasi-stiffness because it's not actual joint stiffness. It's really coming from the musculature around in a dynamic type of way. And so for my master's thesis, I worked on how do we build just very simple models if we considered we only have springs, dampers, torque actuators. How do we build a model of this system that's going to replicate what an intact limb does? And so this is what you can see as this resulting model. So you have a relationship where you go from 1 to 2. So as you hit the ground, you control the movement of the foot onto the ground. So that's our controlled plantar flexion phase here. And then once your foot's flat, your tibia progresses over the foot, and you would move from point 2 to 3. As you push off the ground, you're going to go from 3 to 4, and that's where you actually need to put energy into the system. So that's our powered plantar flexion phase. And then in the swing phase, you just come back to where you started. So we look in this in a variety of different activities, and you can see in this sort of level walking model, you can get away with springs and nonlinear springs. But you see the area under this is this energy that has to be put into the system. So work has to be done. And no passive device can do this active work. And so what this suggests is that to replicate intact ankle function, you have to inject power into the system, or energy into the system. And the amount of that power increases with walking speed. So part of the work I did was just looking at the effect of speed. So not surprisingly, it also changes with stair walking. So I studied people as they transitioned from descending stairs into level walking, and then going into level walking into stair ascent. And developed basically this sort of state model of what it would look like. So if we just took these mechanical elements, how could we represent that behavior? So just you have springs, you have dampers, and in stair descent, you can be completely passive. In stair ascent, unsurprisingly, you have to inject work into that activity. So that was sort of where I left that project, and I'll explain this kind of journey that I went on here. So this was work I did with Hugher, and then his students have taken this on to build schematic models of what this would look like. Then there was a CAD diagram. You have a physical prototype with series elastic actuators. And initially, the prototype used this state-based controller model. As we were talking about, it's definitely changed in the future as a few iterations over time. So there's a physical prototype. What this does is it pushes off, gives you that active push off at plantar flexion. And then this was modified a great deal. So this is Sam Owl's work, and then at Eilenberg, there's changed the controller. And then this is where it became a commercial product. Now, I'll be totally honest with you, I don't know exactly what controller they're using at this point in time. But what I think is really interesting about this particular device is that, number one, it became a commercial product, which is very, very rare in this field. Surprisingly, there are so many great things and so many great technologies that are developed, but so rarely they actually get into the hands of the patient. And so this is one instance where you see something that in a relatively short time frame, from about 2003 to this was commercialized in 2011, you have a product that hits the market. And so I was lucky enough to come back around to this. So where I left it, it was just this theoretical model. And I went and did a PhD in upper limb motor control. And then I worked at an engineering consulting company. I crash tested cars for a few years. And then I went to work for the Army. So it's kind of this very nonlinear route. So for those of you who are students, don't believe that there is only one path. You can certainly leave academia and come back into it at certain points. So I actually got lucky enough to come and work for the Army at a time when they had just commercialized this and they were testing it. And so this is the pretty amazing facility down at the Center for the Intrepid in San Antonio. And you can see this walkway that has 6 force platforms embedded into it. We have an instrumented treadmill here, rock pit, and a full stair set that you can walk up 20 stairs and down. And that entire thing is instrumented as well. So in terms of testing out your device, it's a pretty incredible playground to work with. And so we can see here that if you take this device, and what it's doing is providing, again, that added power at push-off, you can actually replicate, to a certain degree, the plantar flexion at push-off. So this is, in all of these graphs, you're going to go from 0 to 100% of the gait cycle. So that's from heel strike to heel strike. And this here is the ankle angle. So you can see from a passive device to powered, you can get this actual plantar flexion. And that translates to an increase in ankle power as well. Now, in stair ambulation, you can see that you get positive power, but not quite on the same level as what you would get from an intact limb. So it's able to get closer to that performance, but doesn't perfectly match it. And I also worked on studying something this wasn't specifically designed to do, but how does it handle irregular terrain? So what's going to happen when you walk on something like rocks? So we had them walk over this rock surface, and you can see, it increased their walking speed, so it's about 10% greater. The one downside is that when you have push-off power and you don't necessarily need it, you just push down into the ground and kick rocks everywhere, or sand or whatever it is. So there are some instances where you may not want that. But it seemed that these, at least, patients could do fine with it. So they walked faster, and they tended to have pretty normal movement patterns. And so this is looking on the top at the hip, the knee, and the ankle. The gray band represents control subjects, so healthy individuals with 2 intact limbs. And then you have your intact limb and the prosthetic side. And so what you can see from here is that, again, you're getting ankle plantar flexion where you didn't before. You're getting very slight changes in knee flexion, although I would argue those are probably not clinically meaningful. But you don't get any changes here at the hip. So nothing much is changing as a result of the power. So you think the power is coming up the system. It's going to change the full system. But really, we see this focused, localized at the ankle. The one thing, though, that's really important to note is that look at how far they deviate from normal behavior. It's like very little, right? So even when they're dealing with, when they have no power at all, they still have pretty normal walking patterns. And this is because I think, these are all active duty military personnel in their 20s. They're very fit individuals already. They operate at a really high level. And so the question becomes, who are we designing for? And I think this was a really interesting one to look at it at the time, because you think, well, you could enhance their performance, right? But they're already really high. And in this particular device, you can't run, right? So you can't handle the forces associated with running. So for these guys, that was really important. They want to be able to transition from walking to running because they're at that level of activity. And I think this was also my first foray from an engineering perspective into this clinic of like what really matters to the patient. And for some of these, it's like things that you would never think. So if you looked at that device, you have a battery pack on the back, and it's a little bit obtrusive. It's a little bit noisy. So for some people, they wanted to be able to like sneak up on other people. I'm not sure why. This was a big issue, that it's too noisy for me to do this. Or for another patient, and again, I was in Texas, and he said, I cannot wear my skinny jeans and my cowboy boots, and therefore I do not like this device and I don't want to wear it. And so it's like these very distinct attitudes about what it's going to do for you, and then are you willing to kind of take of these other things in your life that you want in order to have that. But for us, it brought up a lot of questions, and it was also curious about how this would clinically translate. So once we went to Michigan, we were looking at, okay, so what we're seeing in Michigan is a completely different cohort of individuals. So these are, again, going to be more of the people who are later in life, who've had their amputations, who are not necessarily trying to go back into active duty. And they're also going to have this fitting done clinically. So it's not something where the device manufacturer, like in the other case, is coming and they're doing the fitting, and they have this specific knowledge of what's going on, the inner workings of the device. And so my postdoc, Emily, ran a study where she looked at basically, what if we just do this in a laboratory? We don't have specialized prosthetists. We're going to get our certification from the company to be able to fit it and test out these individuals we see. So this is what this actual process looks like. So here's one of our patients. I'll admit this photo is completely staged. It was a photo op. You wouldn't necessarily do this, but you have one of our participants here, and this is our prosthetist who has a tablet. So what the tablet is showing you is this plot right here. So this is your walking speed. This is your ankle work. And then if your ankle work falls in the 95% confidence intervals of normal behavior, then you get a green dot and it says good, you're in the right range. So again, the idea is you want to mimic an intact limb. So we want to replace what they've lost. If you look at that, you'll notice that there are some red dots and some orange dots, but those are actually turning steps. And so you may see more power when they're walking at a slow speed, but it's as they turn around in the corners. And so we studied these participants as we did strength testing. We let them accommodate to the device for about 15 minutes. So again, this is a very short period of time, but it's not uncommon from what they do clinically. So they're actually going to tune it. They say, how do you walk? They make some adjustments. They send you home. You may come back with issues, but that's generally how that process is going to work. So we had them come in. They did an overground preferred speed, and then we looked at their energetic cost as they walked on a treadmill. So you can see this is our participant wearing a mask that's measuring his oxygen consumption. He's also got markers on to track his kinematics, and we're also measuring muscle activity throughout this. So they're doing two conditions in random order. So all these people had passive devices and they have powered devices, or have the BIOM. And so we ended up with 10 participants, and 2 of them happened to be people who owned the BIOM already. So for 8 of them, this was completely novel. They had their 15 minutes to accommodate. And for 2 of them, they had had it for a year or 2 years, and they had both devices that they would wear regularly. And so what's interesting about this is that when we look across our 10 individuals, no change. So you give them ankle power, and then say, measure how much energy does it take you to walk. So you're actually injecting energy into the system. And this is our powered condition, this is our passive condition, and there's no change for everyone in terms of that cost. And we were very surprised by this because some of the initial work showed that you'd get this nice decrease in energetic cost, right? You're putting in the power. So why isn't it that they change? Additionally, we see that there's no change in their preferred speed. So they don't prefer to walk any faster. They're going to walk at their own speed, even if you have extra power. And again, that was kind of surprising because previous results had shown they should probably walk faster if they're able to get power in the system. And so then we look at this on an individual level. So right, not every person is going to behave the same. And so when we look at this, you can see some people do improve. So some people, their energetic cost goes down. Some people, it actually goes up. In terms of speed, you see the same thing. And so what I want to point out are there's 2 colored circles. So those represent our BIOM users. And so ironically, our BIOM users had the most extreme differences in behavior. So one of the people who owns this device actually does walk slower with it and uses more energy when he walks with it. Whereas the other one does very well. So they had kind of opposite trends. And this is what we take a look at then and say, okay, so we can now categorize people into sort of what we're calling non-responders and non-responders. And so this will show you, this is their change in cost of transport. So for these people, it was easier to walk if you added power. And this is the change in their preferred speed. And so for those people, they preferred to walk faster, and it was energetically easier for them. Now I want to point out these are two different measures. So when you're measuring cost of transport, it's not at the same speed. It's just that overground, their walking speed was changing. And so generally speaking, we have people in this category, and we have people who are the non-responders. And again, we have the two outlier, or the triangles that are our experienced users, kind of on either edge, which is really interesting. And so one of the big questions we had is, okay, well, what the characteristics of the individual predicts whether they're going to actually be able to use this and get useful power out of this device and be able to incorporate it into the body in a meaningful way. And so this is kind of ironic to me, but what actually predicts this the best is what's something called the K level. So the K level is a classification that Medicare uses to determine who can have what device. And so it's a scale that goes from K0, meaning you don't walk, you're wheelchair bound, to a K4, which is you're an unlimited community ambulator. You can go anywhere. You probably have high force requirements, things like that. So these are your athletes in the K4 category. And your K3 category, these are people who have the potential to achieve multiple changes in speed and to do different tests like that. And this is a measure that the clinician sits down and they talk with the patient, and they talk about what do you want to do, and so it's kind of this subjective thing, but yet it really classifies who succeeds and who doesn't. And one of the things that we think, and I will say this is a little bit conjecture from just having to talk to people, but you talk about then how do you get someone to use this, right? Like if I push down here, it's going to push back, but I have to know like where do I want to put my foot, and like how do I want to apply that load. And it seems like the people that we saw who picked it up quickly had some sort of athletic background. In particular, one was a skateboarder, and he said, okay, I kind of get this, right? So if I'm on the skateboard, I lean my body weight this way, it's going to do that. So if I do the same thing to the foot and put my body weight here, this is what's going to happen. I'm like, yeah, okay, that makes sense. And we have a skier, same thing. So it's knowing sort of how to manipulate your body weight to get something out of the device. Now, I don't know that the K level totally, encompasses that, but I think there's something about kind of knowing how to manipulate these things that some people inherently have and the others don't. And we also looked at a host of other factors. So is it strength that's doing this? It seems not really. Is it their age or their weight, height, residual limb length? The only things that came out sort of marginally are that it's related to, moderately correlated with BMI. So there actually lighter individuals showed more benefit. And there was a very loose relationship with prosthetic experience. But I would say this one's a bit harder to interpret because you don't have kind of something that makes a lot of sense. So maybe if you have more prosthetic experience, then you'd get some benefit. But it seems that one is pretty minor in terms of correlation. And so this brought up a lot of questions. So this is, again, not what we were expecting. So what is it that, if you've put this power into the system, you would think that it would make things easier. So yes, they have the potential to do it, but maybe there are other things. So maybe it's the tuning. So maybe we didn't give them enough power, right? Maybe we should have given them more. Or maybe it's because they just didn't have enough time to accommodate to it. And maybe these things you have to learn over time. So there's this learning process that's going to go on, and they would be able to figure it out. So we've been exploring both of those questions. So this is a study we're doing for the Department of Defense where they are interested in kind of what the outcomes are with these devices. And so we have people, what if we give them more time to adapt? So now we're going to give you 3 weeks, take it home, and see what you do. So hoping to see, like, are they going to change anything about their muscle activity patterns over this time? Eventually, could they use less energy? Would they be able to walk for longer distances? And then would they also maybe help change something about their behavior? So does this enable you to integrate into the community in some way? And so I don't have a lot of data on this because we've got 7 of our 12 participants, so I don't want to show too many preliminary things, but I will tell you kind of just subjectively what patients think about it. Because I always think that's interesting. We have my smiley face here, so here I'm going to tell you the good, and then I'm going to tell you the bad. So the good is, you know, the people said, our participant 1, he says, you know, once he adjusts to the weight of this, so this device is heavier. So a regular prosthetic foot's about 750 grams. This is, I think, 2.8 kilograms. So there's a big difference here. So you're talking about like 1.5 pounds to 5 pounds. So he's, you know, if you get used to this weight, nothing's harder. And then I feel like, you know, I can walk longer and faster. Participant 2 really liked it, said, you know, I feel like I have my ankle again. And for him, actually, it wasn't the powered piece. It was the fact that it has this passive flexion. So when you hit the ground in a normal foot, it stays in that posture. But with this foot, it actually rolls the foot all the way to the ground. And he says, you know, especially for slope walking, that makes a huge difference in terms of the stability. This one I put in italics because it's sort of good and bad, where he's saying, you know, basically I was about to call you up and give it back in the first week because I really didn't like it. And I felt like it was a brick, but then I figured out if I could just contract my muscles, and he points to his quads, then I can use it. So it was like he had to learn how to actually load the device. So if I have to push down, I'm gonna have to use this to extend, and then, oh, okay, now I get the burst of power from it. So 2 of them said the slopes were easier, especially when carrying a load. And then another person said it took about 3 to 4 days to acclimate, and then he felt like it could be easier to walk, take longer steps. So then there's also the negatives. So we had complaints, you know, you need more socks, this device is heavier, and you can get more pistoning, so that's movement of the residual limb in the socket. Someone experienced what he called loss of balance. He did not fall, where he got a burst of power when walking down the stairs. So you shouldn't get that extra burst as you walk down, but he got this kind of burst, and it propelled him forward, and he had to grab onto the handrails. There's complaints about battery life. There's also the issue, so I talked about rocks. You have the same problem with snow. So in Michigan, I mean, Pittsburgh, I mean, the same thing. But we have some of our patients who had this during the winter, and he was out walking in the snow and the ice. And if you get any power on ice, you tend to slide, right? So basically he said at that point, you just have to turn the device off, and then you could get around in the snow and ice. And then we had the one participant who basically said after 3 weeks, he still wasn't used to it. He wasn't sure what it was doing, and he didn't understand it. So he'd had the training in it, but to him, it's sort of, and I think this is this interesting idea of how you feel about this. Is this a part of you? Do you have control over it? For him, this robotic device was very much a foreign object on his foot, and he didn't know what it was doing. And he just like, what is this behavior that's happening? I don't know what's happening with it. And so it's hard to get a sense of like, how do I use this kind of intuitively? And so the next piece we're looking at, and really interested in, is what does this change about behavior? So in the lab, we're looking at level walking, and a lot of, I would argue that, you know, that's a very narrow subset of what people do. And so we're using IMUs on the prosthetic foot and shank to try to see what kinds of activities are people actually doing in the home, and then where are they going? So are they able to navigate around their house, or are they able to actually like get out into the community and go for walks and things like that? And so this is, generally speaking, what we're doing here. I don't know if it will play, but, oh yeah, you can play. So anyway, you see the IMU, and you can actually track where the person's going. So they have a GPS phone at the same time. And so we're looking at the movements that they're making, whether they're going up slopes or stairs and where those activities are occurring. So that's our eventual goal with that. And so that's sort of really how we go about evaluating them, and then also looking at what's happening in the home. Now, the other question we had was about the power, right? So maybe we just didn't give them enough power. So this is based on the idea that you're replacing something that's biologic, right? So you just want to replace what's been lost. And so in this case, you're taking, so here's a healthy limb, and this is the amount of work that that ankle does. And so we can match that, and maybe we assume that's going to be the right solution. But there could be some other solution here, which is actually a better solution for this person if we don't know about it. And so an alternative is to do whatever you can do to minimize energetic cost or some other parameter. And so not assuming that you want to behave necessarily like an intact limb, but that you could do something else. And so this is some work done by Philip Malcolm, just kind of demonstrating what this process looks like. But he has a ankle-foot exoskeleton here, so you have the AFO with actuation force. And he's showing basically you can change the period of actuation and have a direct impact on how much energy that it takes the person to walk. And so here you see this minimum, which would be your energetic optimally solution, so your energetically optimal solution. And so we thought, okay, so what if instead we try to minimize energetic cost? So do these things match up? So is our energetically optimal and our healthy limb intact work, do they actually match? So we ran another study where we had very fit individuals, because this is a long process, walk on a treadmill with full body kinematics and muscle activity, and we measured their energetic cost at 6 different randomly ordered power settings. So in the BIOM, what you can change is the gain. So like I said, the controller is a little bit, it's proprietary, so we don't know exactly what's happening, but you can change the gain factor. So you're not changing the actual amount of power, and this is important. But so we did no power, 25%, 50, 70, and 100% of their gain settings. And then we looked at this prosthetist chosen power, and that's the setting that matches intact limb work. And so what you see looks very confusing, but generally speaking, you can see if you turn up the power, energetic cost goes down. So this is our cost of transport. These are our 5 settings. The filled in circles represent the one that matches intact limb work. And so for most of the people, you can see that there's some setting higher than intact limb work, which is actually going to save you energy. So they can do a little bit better if they get more power. And this is maybe unsurprising because the device itself is uniarticular, it's not biarticular. So you can't exactly match the limb anyway. And you also have losses. So you have losses at the, because this is measuring its approximation of ankle moment, but not accounting for the fact that you have a shoe, and then you have a socket where you get displacement as well. So you can see generally that, but you see it's also not very linear. It's very hard. Everyone has their unique pattern to follow. And so one of our big questions was, this device is actually reflexive. So you're setting the gain, but how much power you get is really based on that, and also how hard you push on the ground. So if you push on the ground harder, you get more power out of it. And so we were just wondering, how do this gain actually work with the amount of power that you get in the device? So this is what the device reads out in terms of power, and this is what we're allowed to change in it, basically, that gain setting. And so what you can see for some of these people, so once you hit 75 to 100, it's not really a linear relationship between the amount of power you're getting. And so this could be a couple of things. So one of them is just that you choose not to push as hard, right? So you have this high gain, so you don't have to push down on the ground as hard, and because you don't want that excessive amount of power. It could also be something about motor limitations, and that we don't know. So I will say, once you take this device up to 100%, it gives you a lot of overheating warnings. It will still go, and they tell us it will still deliver the same amount of power, but it definitely gets very angry with you. So So it's possible that it's also just kind of dialing back on that exact amount of power. And so if we instead look at what this actual power is relative to the cost of transport, you can see that it looks a little bit more of like a linear relationship. So each of these lines, again, represents an individual subject. You can see, generally speaking, as you give them more power, your cost of transport actually decreases. So this is interesting. I think one thing we were hoping for is that it would be more of a bowl, so that you would have some value that, obviously if you gave them too much power, that you have to then absorb it in the body somewhere, right? So we expect that there's probably some of this relationship, but we just may not be able to do that with this particular device. You can't take it out to the limit of where they're actually going to see that, and where you could actually find kind of that divot in the behavior. And so looking at this, if we think about metabolic costs versus approximating that ankle function, you can see they give you different values. In this particular individual, the prosthesis or the intact limb work would give you this cost of transport over here, and that's going to decrease if you give them more power. But prosthetists wouldn't do this because it would say this is not a safe setting. You're giving them too much. And so another question we had is basically, if we do get this savings, where is it coming from? And so we're looking at this on an individual muscle level and saying, which are the muscles that are actually decreasing their activity if you give them more power? And so this is just giving you one sampling of this. This is a video of an individual. So the mannequin leg is the prosthetic side. And you can see the no power to the 100% power setting. So you can see it actually gets a bit more symmetric in terms of the movement patterns and decreases activity in several of the large muscle groups. And so we're still exploring a lot of this muscle activity data right now, figure out exactly what's going on with it. But generally speaking, you can see there is this relationship between how they use those muscles and how much power they have. Let's see if we'll go. All right. So the next question we had is, okay, if we could do this, but maybe we can do a better job. And also, this is a really lengthy procedure. So I didn't get into that, but when you're measuring energetics, typically what you do is you have a person walk on a treadmill till they reach steady state. So that's between 3 and 5 minutes. And then you collect 3 minutes of data at steady state. So that's 8 minutes minimum at each of those settings. And so if you have 7 conditions, this is a really long period of time. And so with David Remy in mechanical engineering at Michigan, we've been working on sort of doing this online optimization. So VO2 data is a very noisy signal. So you're getting a value every breath. So deep breath, taken a lot. You get the shallow breath, you take in less. And so we're taking an average of a few of those breaths and saying, can we filter it, remove anything that looks like an outlier, and then estimate our gradient. So basically what we want to know is, does it make them worse? So did we make it worse? Did we make it better? And then how confident are we that that change is true? So if we're not that confident, we're not going to make any other big changes. But if we're pretty confident, we're going to go in the opposite direction. And so we go with that and then change out the parameter setting. So if we're confident that we changed it in one direction and that was the wrong direction, we come back down, change the parameter settings, and then I'll actually change the parameter settings on the device. So in this particular study, we looked at the amount of power that we're giving someone and the timing that power has been applied. Now, the safety limitation ended up not being a factor because it's actually taken care of in the hardware. So you can't actually change this in any way that device would deem unsafe. So from our perspective, we didn't need to implement anything there. So we had a single subject to complete both this mapping and this optimization process. So this is some of Wyatt Felt's work. So what you see is that here's our timing, and so we changed it from 0 to 100% of this sort of arbitrary timing setting that the device has, which is kind of a window around push-off. So it doesn't mean it's 0% of the gait cycle to 100%. It's kind of this portion of later stance in which you can actually manipulate it. And then change the amount of power as well. And so this is just the parameterization of that. So you can see, they had to do, again, 8 minutes to get each of these dots. And if we do, instead, this optimization, it changes both these parameters and hones in on certain regions. And so what it finds here is that there is a pretty wide region in which it's confident is the minimum, but we don't know a specific value. So in this region, it's saying this is probably good, but you kind of have your choice. And you can see the dots actually agree with that. So you change this parameter in that region, it doesn't make a whole lot of difference. In terms of the power setting, you have a narrower region right at the end, and so it predicts that your minimum is at 100%, which is actually true. Now, the really nice thing about this is that took 13 minutes versus like 48 minutes of walking before. And that 48 minutes doesn't include all the rest times that occurred between that. So that was, a 2-hour block of time, and now it's 13 minutes of continuous walking. And so you can see this surface plot is it's very sparse in terms of the number of points, so I wouldn't put too much into the curvature of it, but these are the dots that we would get from the parameterization. And the idea being, if you have these two parameters and you're looking at cost of transport, you then can search for a region where, with the combination of these two parameters, you find some minimum value. Now, the issue with this is that these landscapes don't have these very nice, they have kind of shallow regions where you have a lot of play in them. And part of this is not being able to have full control over what the device is doing. And so what we're doing right now is we have the Humatech emulator, like the Steve Collins device, so that we can have more direct control over the range in which we can play with these power settings and the timing in order to really perturb it beyond the regions that we can get to with this commercial device. And so hopefully we'll have some clearer maps of that soon. But the idea here is that we're trying to tune complex devices, so something that would have more than two parameters. So we're refining this algorithm so that it will go into multiple dimensions at the same time. So if you think about something like the Vanderbilt leg, it's got 100+ parameters. And so you can't tune each one through parameterization, or you will just be there for months and months of testing. And probably they all interact as well. And so you need some way to kind of hone in on what this correct solution is. And I would argue that, so cost of transport, that's one measure that we optimize for. It's not the only one, and it may not be the most important one for that particular patient. So it could be that, for them, stability is more important or something like that. And so you can change this to optimize to different things. The goal generally is, for me, I think it's this idea of a self-adapting prosthesis, which would be that the device is going to learn you, and not on a quick time scale, not like a changing states, like you're going to walk up the steps now kind of thing, but on the days time scale. So the thing here is that you want to make sure that the time constant for the device learning and the person learning are very different. Because if they're in the same, you're just constantly adjusting to one another. And so this is something we want to happen over time, and so it's going to get to this kind of optimal value as you maybe change weight or you do different types of tasks in your life. And so you'd have something that was constantly tuned to you as an individual. And so if it has time, I'm going to go to my last topic, which is control, which is, I think that control is the new area of this. So that basically, this is the BIOM is an example of a device that it deals with control in some sense. You get to push harder and then you get more power. But you can't then say, I'm going to go up the stairs, I'm going to do something. If you want like direct control over it, you have to go into a muscle level, something like that. Now, the problem with lower limb and muscle control, so you think of upper limb myoelectric control, something like that, you can put EMG in a socket and you can get pretty good signals. This is what the muscle intends. I'm going to correspond motion to that. In the lower limb, that position is changing all the time. You sweat. It's really difficult to get consistent signal day to day. And so this is some work we're proposing. We have a DARPA project to do this in the upper limb, but I really think it has a lot of applications to the lower limb. So this is Paul Sederna. He's a plastic surgeon at Michigan, and he's refining this technique for years to look at what we're calling regenerative peripheral nerve interfaces. And so the idea here is it's free nerve ending. When you have an amputation, the nerve gets cut. And what often happens is nerves send electrical signals. They like somewhere to send those signals. When they don't have a place to send the signals, sometimes they grow back on themselves. So what you get is a painful neuroma. So the nerve has grown on itself. You have this really painful growth. They have to go in and do a surgery to actually cut the growth off the end of the nerve. And so Paul's idea was, well, why don't we give the nerve somewhere to go? So what he did is you take a biopsy from another part of the body, so just a really small piece of muscle, and you suture the nerve to this tiny piece of muscle, and then wrap it up and suture it together. And what happens is, it's very interesting, is that the muscle itself actually dies, and then it regenerates. And so when the nerve reinnervates into this muscle, the muscle tissue will regenerate, and it actually changes its phenotype too, which I think is completely fascinating. So if you've taken it from a different muscle group, you can change it from fast twitch to slow twitch just based on the signals that are going into it. And so they showed this in rats for many, many years before it graduated into to primates and then now into humans. But the idea here is too that we can take a nerve and we can split the fascicles of the nerve. So you can actually get multiple signals from a single nerve. And so here's our nerve, here are the fascicles, and we've got RPNIs on each of these fascicles. So if you went into the nerve itself, the problem is that, and there are implants that will do this. So you have a cuff that comes in. The signal to noise ratio is really poor. And so you have a hard time interpreting what it's trying to do. But the muscle acts as a biologic amplifier. So now you have a much better signal to noise ratio, and you can actually get at what that nerve was doing. So it's still sending signals to these muscles even though they don't exist anymore. And that pathway is still present. And so the real advantages here are you can get large stable recordings. They're functionally selective, so it would be actually what that muscle intended to do. They prevent this neuroma growth, and there's also some recent evidence that suggests they actually prevent you from getting phantom limb pain as well. So that is really pretty cool. And it doesn't involve moving the nerves or de-innervating existing muscles. So for those of you who've heard of like targeted muscle reinnervation, they actually have to de-innervate the muscle and then reinnervate it. And here you don't have to do that. It's just a tiny piece of muscle. And so this is what it looks like in a primate. So this is some work out of Cindy Chestik's lab. So these are in monkey arms. And you can see these are the RPNIs, multiple RPNIs, and then this is the nerve along it. So then we've gotten now into humans. So we've had 4 participants in this study, but actually over 300 have had this procedure done at the University of Michigan. 4 have done it for prosthetic control. So for neuroma pain, what they'll do is do a single RPNI. For prosthetic control, they actually will do multiple. So they break it into fascicles and then create multiple grafts. And so you can see here on our median nerve, we have 4 grafts. On the radial nerve, you have 2. And here on the ulnar nerve, you have 3 grafts. And then, let's see if it's going to play. Oh. So you can actually see this tiny muscle contracting. Can you see that? So the person thinks, I want to move my finger, and this tiny little muscle piece that's at the end of the nerve is actually contracting, and you can see that under ultrasound. And then we can use a needle electrode to go into this and actually measure the signal from it, and then use that for control. So this is what this looks like. This is why you need an X-ray or an ultrasound physician, because these are extremely hard to actually find. But he goes and locates, this is where that RPNI is, and then puts the needle electrode into it. And then we actually get measurable EMG signal from it. So this is, again, EMG that's coming from them thinking, I want to move my little finger. I want to move thumb. I want to do opposition. So they're not doing these tasks, they're just thinking about it. And this is a person who's, I think one of them is 15 years out from amputation. And so these pathways, they still exist and can be accessed. And then, this one's, so the hand is there for demo, but he's actually matching what's on the screen. So the hand goes a little funky at some points, but so it's saying, put your hand in this posture, and he thinks I'm gonna do it, and it tells him like whether this is done correctly. And so you can see this is the setup, so he has needle electrodes going into each of those RPNIs, and it's measuring that and then predicting what he wants to do. And this last one is continuous control, so this one is kind of more fun. So now he actually has the opportunity to move the finger in a continuous fashion, and it's going toward targets. You can see them coming forward. So we're excited about this. I think it's got a lot of potential. Downside right now is, so we have a investigational drug exemption, which is great, so we can actually do the surgery. We are waiting on the nerve cuffs now, so this is another company who's developed an implantable cuff that will go around these RPNIs, so you don't have to keep poking them. What happens actually is that you have sensory nerves in there as well, and so if you continually poke people, it gets very painful over time. And so now we are not going to poke them with any more needles until we can get implantable cuff electrodes that will go around that muscle belly, and they wirelessly transmit, and so that you can read that signal and then control the hand. And so just kind of summarize, take-home message. So basically, powered ankles can work, but they may not be for everyone, and they may not work without ample time for training. We think how you tune these devices is really important for the outcomes you see, and that these parameters may need to change on a continual basis. I think there's still many, many open questions about what you should optimize for, and potentially that could be done, again, on a subject-specific basis, based on their own priorities. And then I really think that giving people direct control over the device could enhance their understanding and their performance. So ideally, this is going to help them learn how to use something quicker because it's coming from their nervous system. And hopefully, if you feel like it's more of your action, that it becomes more part of your body, and that can enhance your performance. So I want to thank all of the people who have funded this work, because it could not be done without any of them. And it also could not be done without any of my collaborators or students, and especially all of the study participants, particularly those who have come in for multiple of our studies. And then finally, I have a plug for our robotics program. So if any of you are recent PhD grads or postdocs and looking for positions, the University of Michigan would like you to know they're hiring in the fall of 2018, and that this is the new building that will be there in a couple years, the Ford Motor Company Robotics building. So clearly Ford is paying for a great portion of this building. But this has a open air drone facility in it, and also we have a self-driving cars facility at M City. So yeah, so with that, I will take any questions you guys have. Mm-hmm.
So the nerve cuffs that you're waiting on, you said transmit wirelessly?
Yeah.
Do you know what the delay is associated with those?
I don't yet, because we haven't gotten them. So there, and it's a reason. So we go with a company that is also funded by DARPA for this project, and they are very close to finalizing the IDE. And so we haven't seen actually the final design yet. We generally know what it's looking like, but until they have sign off, yeah. I'm excited to see it though. Mm-hmm.
So earlier you were saying that the powered ankle was heavy for some of your participants.
Mm-hmm.
Do you know how much that ankle weighs in comparison to a real human, like lower leg?
Yeah, it's actually not that far off from an intact limb. It's just that they're used to devices being much lighter, and then again, you don't have the musculature to accommodate for it. So it depends on what you want to do. It will kind of make up for itself for long bouts of walking, but like some of the patients that we talked to that had it and returned it, it was because they said, you know, in my day, I sit in my chair, I walk 3 steps to the printer, and then I sit back down, and that's all I want to do. And so if that's all you want to do, then it's very heavy, because it's really not going to learn and give you power in that kind of time frame. Yeah. Mm-hmm.
The RPNIs, do you have issues with scar tissue formation in the muscle groups, and has that affected sensor fidelity at all?
Not so far. So I think some of these things are early to say. So it's only been implanted in people for a year and a half, about, and so we haven't seen it yet. It doesn't mean that that won't happen, but in the rats, no. So whether that carries over, I mean, that's a good question. But the reason that also went through so quickly in terms of going through people is just because it can prevent neural pain. So we're questioning it from a prosthetic control perspective, so that's the IDE, but the neural pain is huge, and so if you can prevent that, they're not as worried about kind of the scar tissue issues. Yeah.
So you saw as you increased the gain on the BIOM that in general people's metabolic costs went down. Did their preference for the device also increase? Were they happy at those high gain settings?
Yeah. So interestingly, we asked them about, I think maybe not the best measure, but rating of perceived exertion. So how hard is it to walk? And for many of them, they don't think walking is that hard in general. So we don't see much of a difference there. It's like, okay, it's always kind of the same. But anecdotally, a few of them commented, wow, I really like this, but where others were like, what is happening? This is too much. So, so it would be interesting to correlate what they are able to do in terms of flattening that out by maybe not pushing as hard with how they perceive what's happening. So I would say not everyone thought 100% was great. Yeah. Mm-hmm.
One thing which I was wondering is like in the initial test case of walking, you showed like if the test case knows that how the thing works, it like generally affects the way they use it as well. So like if the skiing person figured out that that particular sort of movement helps them. So like is there a way to explain to them or like have some kind of sort of demo from people who know about how they work and then try to
in terms of the training, like of, you know, how do you accomplish, and I think it's something the clinicians are certainly really interested in, because they said, you know, it's really hard to teach them that, and if there are ways to do it, we would love it. But even something like alignment. So if you take the device and you align it, you change the angle of it or you rotate it. The Prostheses, so some people will notice like millimeter change, and there are others that you could change it like 12 degrees and they'd be like, I'm fine, and they walk out, and then they come back 2 weeks later and they say, my back really hurts. Like, why does my back hurt? And so it's sort of, I think it's some people are just going to take longer to notice those things, or maybe just not as in tune with how they are. But we certainly would love to train it if there is a way to do it. Interested.
Is there no more questions? Yeah, thanks so much for your very interesting talk. I really enjoyed it. I think, Deanna,